Brilliant. Thank you very much. In the great words of Monty Python, and now for something completely different, or not. So we've heard a lot this evening about decentralized file storage and about incentivizing file storage with things like Filecoin. So what I'm about to move to now is something that's actually got a lot of parallels with that. And we're talking about incentivizing and decentralizing AI and machine learning. So good evening, my name is Matt Hamilton. I'm from a company called Bittensor, and I'm going to be talking about the future of AI on the blockchain. But first of all, let's set the scene of where we currently are with AI and some aspects of blockchain. So right now, we're all here participating in a social activity to achieve a goal. We're all here to better understand Web3 and the related topics and technologies around it. So not just from the speakers this evening, but also from the other participants, the talks we had whilst we were eating our wraps just now, and whilst we've been chatting before and after the talks. We registered on Meetup. We've got people here in person. We've got people on the live stream remotely as well. And fundamentally, intelligence emerges from cooperation, communication, collaboration, right? So by doing this social activity, by getting together, by talking about this topic together, collaboratively, we can increase our understanding much faster than if we were doing it on our own, solo. So we could sit and read books and watch YouTube videos. We could, and we will continue to do that. And there's people watching, this live on YouTube at the moment. So, that's all good, and we will continue to do that. But by doing things collaboratively, we can accelerate that intelligence, that understanding, that learning much quicker. So what has that got to do with blockchain? Let's unpack some of the basics about blockchain as well. So blockchain, digital currencies, if you look at what was invented by Bitcoin originally, it was this concept of digital trust and the ability for computers to be able to reach consensus on something. And in the case of Bitcoin, it was about money. It was consensus about balances, about payments, about transactions. And that allows us to build incentive mechanisms for markets that could not really exist before. A decentralized means by which we can incentivize participation and maintenance of the network. And the Bitcoin network is by far the largest aggregation of computing power in the world, and is itself a marketplace for that computing power. So with Bitcoin, you have proof of work. And proof of work in a nutshell involves effectively guessing a random number that fits a particular pattern, right? It's a lottery as to who gets to fill the transactions in the next block on the network. It's what's called mining. And it solves the tiebreaker of the double spend problem when you're trying to ensure that the same amount of cash or the same transaction is not executed twice. So you need to elect a single authority per block, and that authority is responsible for the transactions in the block. So all of the miners around the world, they go about solving this puzzle, and when they solve it, the rewards go to the miner that solved that mined the block, and the rest of all of that effort is basically discarded. It's wasted. So with proof of work, the effort that is gone into, everything that's done there is a means to an end, but in and of itself has no value. Right, this hashing mechanism that all of these computers around the world filling data centers, burning through vast amounts of energy are doing, does not have any value in and of itself. It's a means to an end, right? And that's why, there's other blockchains as well, ones that are more efficient. If you look at payment space, you've got things like the XRP ledger that are much more efficient. You look at things like Ethereum that are moving to proof of stake in order to kind of deal with that sort of thing. But what if there was a way that we could take that mechanism, that incentive, and build a blockchain marketplace where actually all of that work did have value, right? Rather than wasting it, it was actually going towards something useful. What if we could apply that same concept of decentralized, incentivized, permissioned network to machine learning? Well, that's what Bittensor is, right? Bittensor leverages the same innovation that brought us consensus, on things like Bitcoin, but brings it to what we're deeming the most sort of important thing in this sort of fourth industrial age that we're going through, which is machine intelligence, right? Machine knowledge. The hash function in Bitcoin, as I said, is a very concrete function. It simply finds a pattern or looks to find bytes that match a particular pattern. The consensus mechanism of Bittensor has to deal with a far more fuzzy set of outcomes. It has to deal with actually evaluating knowledge. So if I ask everybody here in this room to take, say, a paragraph or a page of Shakespeare, for example, and summarize it down to a few sentences, everybody here would come back with probably something slightly different based upon their understanding. Now, the question being, how do we evaluate which is the best summarization of that data? How do we work out which one of those participants should be rewarded and how much they should be rewarded for their effort? And that's what the consensus mechanism in Bittensor does. It looks at it's a decentralized network, and I'm going to go into that in a little bit more specifics. It's a decentralized network with each participant contributing effectively intelligence, knowledge to the network, and they're rewarded in accordance to how well they are providing that information. So in the same way that if I was to reward people here for how well they could summarize that Shakespeare, then hopefully that would incentivize people to maybe go off and learn more about the Shakespeare to get a better summary and get a better reward, right? So let's just set the parameters of what we're working on at the moment within machine learning. So you can break machine learning down. There's two very dominant types of machine learning. There's supervised learning and unsupervised learning. So supervised learning is the kind of stuff you might have seen before if you've done any machine learning, in which it's categorizing, for example, data based upon that data, a training set of that data being tagged or described. So here's a whole bunch of pictures of dogs. Now go and learn what makes a picture of a dog, right? Here's a whole bunch of pictures of cats. Go away and learn that. And the idea being is that if you give the machine learning algorithm enough data, it will eventually learn what characteristics make a dog, what characteristics make a cat. And you see this in your smartphones when it automatically tags images and says, okay, those are all the images of Matt versus those are all the images of Bob or whatever it might be, right? So that's tagged data. Then the other main thing is unsupervised data, or what is sometimes called, more accurately, self-supervised data. So you give the machine learning algorithm a prompt. So the cat sat on and you ask it, what's the next token that comes back? And it comes back with Matt. Or the quick brown fox jumps over the lazy and it predicts dog. Now, we didn't tell it what the next word is in the sentence. All we've done is given it a whole load of text and said, read through that and try and understand it so that it can come back with a prediction of what the next word is, right? And if you feed it enough data, again, the idea is that it starts to understand sentence structure. What is a verb? What is a noun? Full stops, capital letters. And then with more data, things like thematic understanding, understanding what are the concepts, what are the themes that are going on in that text. So in the case of Bittensor, we're just interested in unsupervised. We're looking at that bottom bit, right? We are trying to build models that understand the world around us. And specifically at the moment, we're working within the language domain. So we're working with text at the moment on that side of things. So we're building a massive decentralized neural network that's aimed at, like I said, better understanding the information in the world around us. At the moment, the current state of the industry is that it is dominated by a number of large players. Players like Meta, aka Facebook, our hosts here this evening, Microsoft, Google, Uber. They're all companies that have dedicated AI teams that are working on these big algorithms, what are sometimes referred to as foundational models. And some of them are truly amazing. I'll show you a demo of some of them, talk about them in a sec. But these kind of institutions are doing it in a very siloed way. They're seeking the computational power of say, Bitcoin, but they're doing it in the wrong substrate. They're building huge, great big centralized data centers to process this and to run their models on. What if instead of solving these machine learning problems with big centralized supercomputers, we leveraged every computer available on the internet? That's what Bitcoin showed us, right? The computing power of the Bitcoin network is greater than the top 500 supercomputers combined. So the scale that we could possibly reach for that sort of thing would mean we'd have a lot more availability to train much larger data sets. So let's take a couple of examples from OpenAI. You might have seen people, especially say on Twitter, posting images from something called DALL-E. So DALL-E is a machine learning model it's an image generation model. You can give it a description and it will produce an image. So if you say, I want a picture of an astronaut riding a horse on the moon, it will give you an image, right? It's quite mind-blowing what it can come back with. You can describe all sorts of things and it will come back with them, right? Codex on the right is used by a product called GitHub Copilot. I don't know how many people have seen Copilot, but Copilot is a tool that uses AI to understand code. So as you are writing code, it can be pre-filling things in. So you might write a description or a comment, and it will give you the method signature. You might be able to start writing the body of the text and of the function, and it will start helping you and filling stuff in. But what's amazing is it can actually understand the semantics of the code as well. So you can say, I've written this in Python, please translate it to JavaScript. And because it actually understands the concepts behind the code, it's able to do that sort of thing. So it's able to understand, like, one language might have a construct, a while loop construct, whereas another language might not have that as a high-level construct. It might be like a for loop and then an if statement with a break in it, for example. And it can start to understand these higher-level concepts and do them as well, which is pretty cool. So the problem is, OpenAI, those examples I gave, OpenAI is a for-profit entity whose major investor and commercial partner is Microsoft. The models they're building are so large that they can't easily be distributed or run easily. The amount of computing power you would need to run these is well beyond what you'd have at home. So they're only accessible via permissioned gateway and an API. You have to apply for an account and an API key and use them in accordance with a usage policy that they make you see. So not very open. The cost to perform a single training model on something like GPT-3, which is a very advanced text transformer model that's actually used in DALL-E for the language processing, is reportedly $12 million for a single training run. So as a researcher, you're not going to make a few tweaks and kick off the CI and get a build coming out the other end, right? Or you might do. Might get a very big build turn up. So it's taking many months and many millions of dollars to train these algorithms. So as a result, models like GPT-3, they're owned by OpenAI, and they kind of keep them very close to their chest for that reason. They've invested a lot in them, and they allow access just via an API. So it's a permission system. If you want to contribute to the model itself, unless you are part of OpenAI, you can't really do that. But the speed and increase of computational power has far exceeded that of the increase in developers and researchers. So computational power is going up, so following Moore's law just about, and the complexity of these machine learning models is also going up sort of exponentially. But the number of people involved, the researchers and developers, is not going up at nearly the same rate. So what we need to do is scale not just the technology side, we also need to be able to scale the human side of machine learning research. And that's what Bittensor is solving for. Not just the technology scaling, but the scaling of the research and development, as it's a decentralized network that anyone has an equal chance to contribute to. So you're not just relying upon a set of employees at one of these large institutions or a set of researchers, but somebody sat in their bedroom on the other side of the world is also able to contribute. And they're financially rewarded for their contribution as well. That's what things like Bitcoin, Ethereum, the XRP ledger, gave us in terms of financial networks. What if we could do the same thing with machine learning as well? So currently we've used this incentive to scale a network up to about 300 billion parameters, which if anyone's involved in AI, it's a pretty large size there, and across about 3,500 nodes and growing. So like I said, currently a lot of machine learning is done in these sort of siloed models. So the model that OpenAI is generating is different to the model that Google is working on, different to the model that Microsoft is working on. And so some of the research is shared in in papers and what have you. But the actual training and development of these models is not done. So to train these models, you need to feed them vast amounts of data, and that's not something that they're necessarily sort of sharing in the process of developing. So how can we make that more collaborative? Well, the idea is by using an incentive and the fact that anybody can join the network and participate, we can actually make it more scalable. So rather than what happens with typically within sort of academic research, in which it's sort of winner takes all, and there's a prestige and prize of getting your research done, we're going to make it a lot more equitable, and anybody can contribute to the network. So what if you could take a model like GPT-3, which again is a text natural processing model, and instead of training it from scratch, so starting with nothing and feeding it the entire internet's worth of data to learn from, you can actually build it from the previous version, say GPT-2. Or what if you take that on to the next version of GPT, or the next language model? And so we can build these collaboratively based upon other models on the network. And in that way, information and kind of intelligence effectively compounds. We're learning, acting collaboratively, just very much as we're doing here in this room today, learning from each other. So we're building this big decentralized network, and it's incentivized like Bitcoin. It's peer-to-peer, anybody can contribute to. And you might have, say, two different machine learning models in different institutions or different companies. So you might have one of them that's being trained to learn how to detect cars, for example. And then you might have another one in another company that's learning to detect buses. Well, if you're doing image processing to detect cars and image processing to detect buses, then there's some commonality there. Both models are going to need to know what wheels are, what roads are. A bus or a car is a particular, size and shape sort of vehicle, right? It's not a cat, it's not a dog. So the idea is that these machine learning models on Bittensor can learn off of each other. So one of them might understand, okay, this is what wheels are. The other one might understand or start to learn, this is what roads are. And they effectively share their knowledge between each other and learn from each other, rather than necessarily having to train from scratch. Same way that, if I got everybody in this room and asked you to, instead of just studying Shakespeare, you actually studied different texts, and you all came back together and said, well, this is what I learned about this, and this is what I learned about this one. And we share it rather than each having to go off and learn from scratch. And not only that, we end up increasing the diversity of the data, which makes these models more robust, right? So even if people are running the same model, they might train it with different training data. And back to our example of dogs, you might only have trained it on a certain number of dogs, and somebody in another part of the world has a different breed of dog, and it goes, I've got no idea what that is, right? So, but they might have trained it on that as well. So your model might now know what that dog is because their model has learned it. And that's going to make all of the models more robust and be able to, there's a certain number of kind of attacks and vulnerabilities that neural networks are subject to, and this can actually make them a lot more robust as a result of that. And value flows directly to the creators. It's much more democratic. So rather than just employing or going to researchers within these large institutions, anybody can contribute, anybody can be rewarded. And there's a green aspect to this as well, that in sharing the knowledge, you don't have to retrain completely from scratch, right? So you can take an existing model and build up from then. We've heard the phrase standing on the shoulders of giants. And in the case of open source software development, it's a very common thing. We're used to taking libraries that other people have built. We're used to, forking something or contributing to it or working with it. And so let's take the same approach. What if we could build neural networks in the same way that we build open source software and all learn from each other? So how does this work in a practical sense with Bittensor? So there's three different entities on the network. You've got clients, validators, and miners. So if I start from the right-hand side of the slides there, the miners are the ones that actually run the neural network models locally. They produce the representational knowledge. They're the ones that actually learn from the data and learn how to understand what that data actually represents. They're understanding the sentence structure, the grammar, what is a noun, what is a verb, etc. And they're building that representational, understanding of it. You have validators. So the validators are curating the knowledge. They are the ones that are actually, they send the queries to the miners process them, the miners send their understanding of the, back, and it's validators that try and establish who has the best understanding of this information. And then it determines through the consensus mechanism, the validators determine who gets rewarded and how much they get rewarded. So the idea being that the miners that produce the best knowledge and the best understanding get rewarded the most, right? And it uses we've got an internal currency called TAO. And currently Bittensor is a blockchain built on Substrate, which is part of Polkadot. And it's a solo chain at the moment, but one of the things we're working towards is actually joining as what's called a parachain onto the main network. And that will allow the token to flow on and off the network and to things like decentralized exchanges. The tokenomics of the network of TAO actually follows the same as Bitcoin. There's 21 million TAO in total. There's a halving every 4 years, the same kind of model as Bitcoin. So, as a lone researcher, like I said, at the moment, you can't really contribute to some of these state-of-the-art models, right? And there's no incentive really to do so as well. It's very difficult for you to get your changes accepted or published. But with Bittensor, anybody can do, and they can get rewarded for doing that. And the clients, the final one, the clients are the entities that actually are querying the network, right? They're consuming the knowledge. So they're able to pay for that using TAO. So instead of having to go through a permissioned gateway like you have to do with something like DALI or GPT-3, you can actually go directly to the network. You can run a node yourself and supply a small amount of TAO or contact an existing running node and go via then. But that's the bit that's kind of bringing Web3 to AI. It's the decentralized, permissionless aspect of it. Means anybody can not only contribute, but anybody can query and use the network. So a little bit of an example here. So this is going to be a screencast of a Python notebook running and querying a machine learning model. So if I start it there. There we go. So we're importing the Bittensor libraries, and we're syncing what's called the metagraph. We're connecting to our testnet, which is called Nobunaga. And you can see it synchronizes with the network. We then, the next line down below, create a wallet. I've got a test wallet that I'm just using here. We select the network. So this one's 55, which is a model from an entity called Eleuther. And we are, let's go quite fast here. We're sending a sentence. The quick brown fox jumps over the lazy. It sends it to the network, and we get it back. We can run it through the tokenizer to get the results back, and we get the prediction dog, right? So it's understood what that is. So we're then doing another one here. So this is using, just quickly, just restarted that. This is using a thing called synapses. This is why this is on our DevNet. So we're still working on this functionality. And using synapses is a mechanism that allows us to access the network in various different what are called modalities, right? So we can ask it and say, give me one token back or give me a sequence of tokens back, sequence of, what are the next words that are going to be. But it also sets us up for being able to deal with images and video sort of going on into the future. But the second one here, we are passing in the quick brown fox jumps over the lazy, and we're asking it for a sequence to come back. So it goes off to the network, and it's going to come back with a sequence of what's coming up next, right? And it runs it, and we get back, and we get the quick brown fox jumps over the lazy dog and runs away. I don't know what to do, he says, but I can tell you what I think about. I don't know if I want to go to the zoo or not, but I do know that I have a lot of friends that are going to be there for me. So this, like I said, this is running, and then it halfway through sort of seems to deviate into Russian. I probably should have checked to see what that says. Yeah, so what this is, like I said, this is running on a testnet Nobunaga, and the testnet only has a small number of miners on it. So its actual level of intelligence is actually relatively small, but as you can see, it's already, started to come up with something that makes sense to a certain point. And especially if your fox is a slightly neurotic, or I'm trying to think of the right word. The fox is, they don't really know what they want to do, really. So anyway, so that's a demo, and that was, like I said, I could actually run that live. I recorded it just for the sake of demo gremlins. But that's an example of querying against the network. Nobunaga. So what's coming up? So synapses, that's what I've just sort of demonstrated there, allowing multiple modalities and easier inference on the network. At the moment, you can do inference, that's querying the network. But what you get back is basically a bunch of stuff that's really only readable. You get back what's called a tensor, which is basically an array of numbers, which is really only, you need much more post-processing to make that useful. Synapses will give you what we saw there, the actual tokenized output come back. And it's a common format for all models to use. So we can actually have models that, like I said, process images, process text, video, etc. And then the other thing I've also touched on is parachains. So we're going to be connecting to the main Polkadot chain, hopefully later this year. And that then allows the currency TAO to be traded, access to DEX, etc., etc. There we go. So thank you very much. And if you scan that QR code there, that can take you to links, or you can go to bittensor.com. That'll take you to all the links. There's we've got a Discord channel, take you to our GitHub, etc., and my contact details there as well. Oh, and one final thing before we go to the questions. If anybody afterwards comes up and the first person to kind of tell me who or what is Yuma Rao, I've got a t-shirt to give away. So there's also stickers out there, but there we go.
Thank you, Matt. That was absolutely fantastic. I think we should go to any questions that are in the online chat, if there are any.
Just someone asking, when's the IPO? So you can buy TAO on the it's not available on any public exchanges yet, but you can, people are interested in buying it on the Discord channel. There's a few people that buy and sell sort of peer-to-peer on there. So, and someone's asking when Bittensor Playground. So a lot of these AI tools have what's called a playground that you can go on and you can, type in your query and it comes back with something. We are working on a Bittensor Playground. So we're hoping to get that going. We're getting synapses running first because that's the first precursor to that. And then we'll have a playground going on there as well. But that should allow you to kind of go along and have an interactive play around with it. Or you can, like I said, set up your own infrastructure, set up your own, because it's decentralized, anybody can connect into the network. But the playground will just make it a bit easier for people. Yeah.
Brilliant. I think because of the time, I really want to get this sort of wrapped up here. So we're going to go to a break. So we're going to finish here, speak to Matt afterwards. Yep. I want to say a massive thank you to all the speakers that have attended today. I'd love to give them a round of applause. And a massive thank you to everybody who has turned up today to the first London meetup here. Yes, please do come along to the next one. I'm going to be hosting this monthly, probably at the end of every month. The next one's going to be on DevOps. So if you or anybody that you know would like to be a speaker for that one and be involved, please do reach out to us at London Reactor at Microsoft.com. That's wrong. Don't look at that one. Yeah, thank you ever so much for coming. And I think we'll wrap up. If you want to catch Matt afterwards, please do grab him out there. We've ordered a lot of food. So if there's any hanging around, grab some, please.